little bit improper.
Nice to meet you here in person. Nice to meet you on Zoom for people that are following us from their home or their offices. And so I will start with this title that is a bit old, I'm sorry, but it was supposed to be my talk in the first idea, the first, very first program. So in the first, at least 2 years ago, maybe 3. And so what I'm going to talk to you about today. Oxygen 17 plus proton and aluminum 26 plus proton. So two reactions belonging to the hydrogen burning networks, and in principle two reactions that are not supposed to provide us, or maybe to provide to the stars, energy. In principle, they are reactions devoted to, let me say, nucleosynthesis purpose. So they produce isotopes of oxygen, and they destroy isotopes of oxygen and aluminum, and not of the most abundant isotope of these two elements. But these reaction processes are very sensitive to the temperature. So the abundances of aluminum 26, as well as the abundances of oxygen 17, are good thermometers, so good probe to give us information about the nucleosynthesis environment. In particular, about low temperature nucleosynthesis environments, as they are AGB stars. And how I'm talking to you about AGB stars when I'm not talking about S-process nucleosynthesis? Well, because these stars are supposed to be the most important producer of oxygen-rich dust in the galaxy. The AGB star that usually we talk about when we are thinking about S-process or neutron capture nucleosynthesis are usually stars with a mass between 2 and 3.5 solar masses. And these are usually carbon-rich. So in their envelope, the carbon over oxygen ratio is larger than 1, equal or larger than 1. But there should be AGB stars that are oxygen-rich. They have to be very small, I mean, smaller than 1.5 solar masses, more or less. Please remember that this number depends on the stellar metallicity, so the initial composition of the star. Or they can be a bit more massive, maybe 4, 5, 6 solar masses. In the first cases, they do not undergo a large number of Turdroj episodes, so the envelope is never enriched in carbon. In the second case, the carbon in the envelope is destroyed by the high temperature of the bottom of the envelope itself. In any case, AGB stars are dusty stars. A lot of dust in their envelope that make them, let me say, ugly to be observed, but then give us the opportunity to study them in a laboratory. Actually, the dust in the stellar envelope is spread away by the stellar winds. And in some cases, this dust becomes grains included in pristine meteorites. If I have a piece of meteorite fell on the Earth, I can cut it, clean it by chemical approaches and different techniques, and by mass spectrometer analysis, I can have information about the isotopic composition of the star from where the grains come from. And there is no telescope able to give us precise information about the isotopic composition of a star. So grains provide us a very important instrument to give us information and to know what is the isotopic composition of the star in which this dust forms. Just remember, if a star is carbon-rich, the main part of the solar grain are silicon carbide grains. Instead, if the carbon over oxygen ratio in a stellar envelope is larger than 1, oxide grain can form. I highlight in the balloon the thick or the oxide grains that come from AGB stars, and we will focus on this plot. So the grains, the oxide grains of group 2 that are inside the blue loop on our right. They are essentially made by two elements, aluminum and oxygen, plus some silicate or maybe some magnesium, because if the aluminum in star was an aluminum 26, it has time enough to decay and become magnesium. But the structure of the crystals of the SiC will be, of the grains will be in any case made of aluminum and oxygen. So a bit of history about oxide grains. Oxide grains have started to be studied from the beginning of the 90s of the last century. And since from the beginning, it was clear that stellar model and stellar modelists were not able to fit their abundances, but adding some mixing, some extra mixing episodes, phenomena to their models. Why it's so? Because I hope you can see the arrow from home. Okay, this line over there, sorry, this black line here marks the abundances of oxygen isotopes in the stellar envelope when a star is approaching that red giant phase. I mean, a star during the main sequence burn hydrogen. If it's massive enough, maybe it can burn also some CNO cycle. And then at the end of the main sequence, when the star leaves the sequence and start to climb the giant branch, that was the first important mixing episode in the life of a star. It's called the first reject. Some ashes of the hydrogen burning is brought from the interstellar layer to the stellar envelope. And in that case, the carbon, nitrogen, oxygen isotopic ratio in the stellar envelope are modified. And so a star approaches the giant phase with an oxygen 17:16 and oxygen 18:16 ratios that depends on the temperature of its hydrogen core burning. I mean, it depends on the stellar mass. And according to the mass, we have a long series of spots along this line. The smallest mass, the medium mass stars, and then a bit on the back, the biggest stars. But the grains were found to be in this region. So how can the oxygen 18 amount in the stellar envelope can be diluted? It can be diluted by some extra phenomena. And since from the beginning, the people start to say, okay, it should be hot bottom burning. It means the stars are massive enough to have at the bottom of the convective envelope a temperature high enough to allow some proton capture to take place. So there is some extra burning of oxygen 17 and oxygen 18, and their amount will start to be smaller. I never talk about oxygen 16 because in any case, I'm talking about relatively low mass stars. In any case, we are well below the 7 solar masses, and so no oxygen 17 gamma reaction can occur. The other option is stars are very low mass stars, so their envelope are cool, but it is possible that some diffusion, some not convective mixing may link the hydrogen burning region with the stellar envelope. This process that was called cool bottom process may in any case able to modify a bit the abundances of oxygen 17, oxygen 18, perhaps aluminum 27, for sure carbon 12, carbon 13, and nitrogen. Then the question, do oxide grains come from stars with hot bottom burning or with cool bottom process, seems to have a final state in the 2008 when according to a new measure of the oxygen 16p gamma reaction, it seems that it was clear that no hot bottom burning could reproduce the abundance of the grain. So I was happy because I'm close to write my PhD thesis. And with this plot, I was so happy to say, okay, yes, good bottom process can well account for grains. And thanks to some new nuclear physics input, we also have no problem of having forbidden area or region in which the hot bottom burning is required to take place to account for the grains that they stay in this region. Okay, after 12 years, 14 years, these are the two mixing model suggested literature, so cool bottom process and hot bottom burning. And we are focusing actually not for the famous mixing episodes that affect the process nucleosynthesis, but just to the tiny ones that seems to connect the hydrogen burning region of the stars with the envelope that is just above. The question was, and the question for which the mixing mechanism has been investigated for a long time, is that if it's possible to have just one model that is able to account the constraints coming from this process nucleosynthesis, as well as the constraints coming for the hydrogen burning nucleosynthesis. By the way, pay attention to this plot. When we talk about cooled bottom process, we are thinking about some conveyor belt mixing model that from the stellar envelope go down in the inner stellar layers and back up again. In doing that, the materials, the transported materials, are cooked because they come from some place where it's relatively cold to hot place and then back. The idea now is instead to add a third mechanism. I call now here a bottom-up mixing. So the idea is that not to have a circulation, but just some mechanism able to trigger the upflow of some materials. And if we have an upflow, we also need to have some downflow. In that case, the mixing mechanism I'm thinking about is the magnetic one suggested by Maurizio Busso et al., in which is the stellar magnetic field that powers this upflow of materials. What I want you are thinking about now is just to have a fast advective mechanism. It can be driven by the stellar magnetic field, by gravity waves, whatever you want. What is the important thing? The important thing is we have now hot material that from the region where the hydrogen is burning, so at relatively hot temperature, is brought directly in the stellar envelope. So we have not something that is cooking along the way. It's just something that comes from a hot region and is brought in the stellar envelope and mixed. Okay. In doing that, what we can do, we can move portion of material that has exactly the composition of the hydrogen burning shell into the stellar surface. And of course, it will be mixed and diluted. In doing that, as you can see, we have no more forbidden area, as it was for the classic cool bottom process, and even the region of the hot bottom burning is now covered. You can see this plot here is nothing but the updated version of this one. This one was published by Dollet et al. In the 2003. This one was published in the 2017. More grains because, of course, people have recorded much more data on meteorites. But as you can see now, the area where we have group 2 grains, so the red spot, is completely covered by mixing model, and there are no grains over there in which we have no match from the model. And if we now move to look at the aluminum, that is the other isotope element we have in this grain, the model, the curves on the model, well overlaps even all the aluminum 26 and 27 isotopic ratio measured in the grain, even the largest one that are the most difficult to be reproduced. So everything is fine. Why we have to talk about oxygen 70 plus proton reaction? Well, because if we look at the linear cycle and we write down some equation that give us the abundances of oxygen 17 and oxygen 16 abundances in the equilibrium condition, we can find that this is not but this curve. This is the oxygen 17 and oxygen 16 isotopic ratio as a function of the temperature. It depends by nothing but the reaction rate. Good. And as you can see, these are the oxygen 17 on oxygen 16 isotopic ratio recorded in group 2 oxide grain, and we have a good match in a good range of temperature. Unfortunately, in this range of temperature lies at least 2 or 3 solar masses of red giant star burning hydrogen. So the same value of the oxygen isotopic ratio can be matched by stars burning hydrogen at different temperatures. So by stars with different masses. And to increase our entropy, if we are looking to other reaction rates in literature, these ones are the ones by Iliadis et al., we discover that this line can be pretty different. I do not add the error bars, the error region, the uncertainty region, just to give you a good imaging. But as you can see, it can become difficult or easier to match the grains abundances according to the nuclear physics input we use in our calculation. And looking at the oxygen 70 plus proton, the most important resonance that affects the rate in the range of temperature of our interest is the one at 65 keV. It has been measured several times by direct and indirect technique for what concerns the oxygen 70 plus alpha reaction rate. As you can see, the oxygen 17 P alpha reaction is also the one that dominates the oxygen 70 plus proton reaction in the stars, since the rate is at least 2 orders of magnitude larger than the P gamma channel. It's something strange because usually it's the opposite, but we do not mind about that. But for the fact that the oxygen 70 P gamma and the strength of the resonance at 65 keV for this channel has been directly determined, maybe it's just once, that is the one here, the estimation reported by Luna. In the other case, it has been computed or determined by indirect technique. Now, all the data in the past seems to be more or less in agreement, but today it seems that this rate seems to be a bit enhanced. So at the moment in literature we have two nice we have two nice ways to reproduce grains abundances using the bottom-up mixing in Loma stars and a devoted set of inputs, nuclear physics input, that are more or less the one determined by indirect technique, or using off-bottom burning in intermediate mass stars using more or less the nuclear physics input measured underground, directly and underground. What is better? We cannot say. Remember, I have not so many times, so I am not back to discuss about the abundance of oxygen 17 on 16 by which a star approach the red giant phase. But this curve here and this curve there was very affected by the re-estimate of the nitrogen 14P gamma reaction. It was really affected, means a factor of 2. Now, there are small changing about the so-called stellar mass progenitors, or where the different stellar mass lay in this line. by using the last published Oxide 17O+p reaction rate, but it was not so strong because we are looking to this part of the plot, so quite far from the initial value, okay? So if you use the, let me call the direct, so the direct data set, so I would say the Luna data, or we use the THM or the indirect nuclear reaction rate, we can, in both cases, provide fit to the grains. In this plot, what I call A are the calculation of nucleosynthesis made by using direct measurement of the oxygen 17 plus proton reaction rate. The set B instead are using indirect method measurement data. The blue curves is with low mass stars with bottom-up mixing. The red one, intermediate mass stars where hot bottom burning is okay. The blue lines more or less succeed in meet the red spot, so the grains, independently by the nuclear physics input we use in calculation. The red line instead can succeed to meet just a small portion of the grains, and only if you use input data of sets A. So is hot bottom burning not able to fit these grains? Well, if we use the model as plot here, yes, it is. But if we look with attention to not only the oxide grain, but also to the stellar observation, this red point over there, this plot over there are the oxygen isotopic ratio measured stars. Or if we look at another kind of dust that are silicates dust, we can see that in principle, oxide group 2 oxide grains, so these here, are not overlapped, nor by star, nor by silicate. So an idea is that these grains are so poor in oxygen 18, then their abundances is not their real abundances, because once they were analyzed, they were coated by the bulk of the meteorite in which they were, and so their abundance is false because it is due to a dilution of solar system materials with an average abundances, plus the abundances due to the progenitor star. If it's so, when we try to fit these grains, we should also take into account by this dilution effect. So, in the conclusion of the paper by Lugar et al. 2017, the first answer is yes, if we use the new oxygen 17p alpha reaction rate, the fit to the oxide grains due to hot bottom burning is better, is improved, right? But if we want to fit all the grain abundances, we have to add to the solid line the dashed one. That means we have to dilute the composition we have from our calculation with the abundances of the solar system. So how can we state if oxide grains come from low mass stars or intermediate mass stars? We have to look into aluminum and not only to oxygen. Indeed, this is the fit we have to the oxygen versus aluminum isotopic abundances in a classic Cool-Bottom process calculation. This is the fit I just showed you in the previous plot made by hot bottom burning model. As you can see, in both cases, there are a portion of grains, the most rich in aluminum 26, that are out from the region covered by the models. It seems that the problem should be solved if we instead use a magnetic mixing, or what I called you before, a bottom-up mixing. Because in this case, we have some portion of very hot material that come from the inner layer of the hydrogen burning shell, directly exposed into the stellar envelope. And since the amount of mixed material is very small, we have now a feedback on the energy balance of the star. But that is a solution that can come from stellar physics, can be very well mimed or substituted by more efficient reaction rate for what concerns the production of aluminum-26 or the destruction of aluminum-27, or again, a less effective aluminum-26 plus proton reaction, which is the destroyed channel in the hydrogen burning scenario. So this is the situation. Here we have the aluminum-26, here we have the aluminum-27. I do not spend time in the channel of aluminum production, so I will assume that everything is right for what concerns the magnesium plus proton reaction, and I'm pretty sure that is not, but by the way, it was not the title of the talk, and I'm focusing on the aluminum-26 plus proton reaction. In past literature has been underlined several times that because of the uncertainty by which we know the aluminum-26p gamma reaction, that is the dominant channel, in principle the aluminum-26 amount synthesized by AGV stars can be modified up to 2 orders of magnitude. This I'm showing you is the summary of a paper that has been just accepted for publication, and a work that has been done in the framework of the KTEC project. It was a paper whose title was Progress on Nuclear Reaction Rates Affecting Stellar Production of Aluminum-26. Concerning AGV stars, so the relatively low temperature hydrogen burning, this is the sketch of the resonances that determine the aluminum-26p gamma reaction for the ground state. So please notice that the last one experimentally known is this one at 128 kV. Definitely too hot for red giant stars, maybe good for nova burning. But the problem is that this seems to be the resonance that mostly affect the rate. But what about all the resonances below? You can see a list of at least 4. Let me see that at least 2. So this one, maybe this, obviously that, has to be measured with high precision if we want to have some reaction rate precise enough to solve the problem of who produced the aluminum-26 of oxide, group 2 oxide grain. Please notice that the temperature we are interested in are just in this small area here. This is the comparison between the green lines that are that is the reaction rate published by Liadis et al. Instead, in orange, in the colored scale, there is the reaction rate of the StarLib compilation. But as you can see, at low temperature, so this region over there, we have no differences, almost no differences. And the situation is even much more unknown, let me say, for the isomeric state of aluminum-26. Now, aluminum-26 ground state lives for 10 to the 5 years. So it's almost stable for our point of view. Aluminum-26 isomeric state instead has an half-life of a few seconds. So Sandro is looking at me and say, okay, it's not a problem. For us, it's just magnesium. And this, as usually we run our nucleosynthesis calculation. But it was not so. Here again, we have a long list of resonances, and that time they are completely unknown, let me say, that go from the one at 147, that is the most important one, down to one at 3.5 keV. Now, maybe Angelo or Sergio, I don't know, later we talk about Pandora and the possibility of measured the half-life of radioactive nuclei in plasma. I have no idea if the aluminum-26 isomeric state can be a longer lived in a plasma condition.
We have these resonances in a different type of measurement, beta delay, proton decay, and the spinel parity. I mean, parity is plus, but the spinel is not 5 half, it's 1/2.
Okay.
For both 147, funny, 146, and 208. The fact that we see them and beta delay, proton decay makes sure that the spin is 1/2.
Okay, thank you. I will remember it for the proof. Sorry, I didn't write the table, so thank you very much. And what has been measured so far recently do not concern the aluminum-26, but the aluminum-27. These are just the last results we got by Trojanor's experiment performed to measure the aluminum-26p alpha reaction rate. What it has been discovered essentially is that due to the investigation of the low energy resonances, the reaction rate seems to be about 3 times lower than was thought before. In principle, that means, okay, if it's smaller, if the rate is smaller, we will save much more aluminum-27. And this becoming a problem for us, because if we have much more aluminum-27, the aluminum-26 on 27 ratio will be smaller. By the way, here is one of the cases where you have a very nice measurement. And when you put it in your stellar code, you obtain almost nothing. What is this? What's the problem? The problem is that the aluminum-27p alpha channel is smaller than aluminum-26p gamma channel that dominate the aluminum destruction and in the temperature range of hydrogen burning. In estimated this, in measurement again this rate, what we had is that the aluminum-27p alpha rate is even smaller than the aluminum-27p gamma. So we cannot appreciate any effect when we run low mass stars calculation. There is a smaller effect that can be in any case appreciated in running intermediate mass stars. In that case, we discovered that in 4.5 solar masses, the amount of aluminum-26 in the stellar envelope is a bit larger. Not so large to have very important results, but in any case, we can appreciate the effect. And please notice that we can appreciate the effect here for the model affected by hot bottom burning, not from the abundances inside the hydrogen shell. In that case, we have no important effects. So I hope that we will have a stronger smaller aluminum-26p alpha and p gamma too. I have no idea what is going on. And let me just conclude with this slide that is, okay, it's a Christmas slide because I want also to wish you the best for the next holidays, but low mass stars seems to be good progenitor of oxide group to oxide grain if they are affected by a bottom-up mixing, advective mixing. And it seems so because our model at the end are not so affected, the fit of the model is not so affected by the changing of the nuclear physics input. In any case, we provide a fit to the majority of the grains, but we have to use exactly one kind of mixing to fit also aluminum-26. Hot bottom burning models provide a good fit just for a portion of grain, and according to the nuclear physics input used for the oxygen 17 plus proton reaction, the fit should be improved very much. And aluminum 26 seems to not be well fitted. It's important in any case to pay attention by the fact that dilution effect may be present in the formation of the solar system, and the question is still open. What is important to remark here is that both aluminum 26 and oxygen 17 are thermometers, are very good probes for the nucleosynthesis environments. But if we want to well calibrate these probes, we need very precise inputs, in particular for aluminum 26. I'm pretty confident that in the next years, the data about oxygen 17 plus proton reaction will be set at some point, thanks for our matrix calculation and the end of the last data analysis that are now ongoing. So many thanks for your attention. And I am in a school that is not right, but in any case, I would write you many thanks at the end of my talk.
Thank you. Question?
Yeah, I'm gonna turn this microphone on so that the people online can hear.
Thank you. Just a question from a nuclear physicist. So you were talking about this dilution when you were talking about these grains. How do you determine the dilution factor? Is there any model, or is just arbitrary? Is coming from the fit of the data? What is the procedure that is used in these cases?
Okay, this is something difficult because this comes from discussion between physicists and geologists. Okay, so that is the first problem. It is an arbitrary factor, is a free factor, I would say, because the problem is that when you have grains in a meteorite, you have to extract them by cleaning them by acid.
No, but I mean the dilution factor,
the dilution
I guess,
factor
in the mixing.
You mean this?
Yeah, you were saying that, no,
factor?
I think it is the previous slide, maybe. So, no, yeah, somewhere
okay,
here.
This dilution factor, if
you said that to get this dotted line, you need to add some dilution.
Yes.
And so how do you determine this dilution?
No, they are just, it's a free parameter. So as you can say, this dilution comes from 1 to 15%.
And how you determine it?
You have to perform an average. You have the output of your model, the number for your model. I would say these are the stellar values. Then you have the abundances on the solar system, and you compute an average. So I assume after this is the minimum oxygen 18 and oxygen 16 I can have by my model. Then if I add to it 1% of material with solar system abundance, I move from here to there. If I have the 5%, I move here, the 10% here, and so on.
But why not 0.01% then?
There is no way. You are just
okay.
a poor astrophysicist that try to match the constraints and try to do your best.
So it's arbitrary, essentially.
Absolutely, yes, because you cannot say how well the separation between the meteorite materials, the bulk materials, and the grains have been done in laboratory. You have to try, okay, how worse was my technician in laboratory? Maybe yes, because if you have something that has no oxygen 18 at all and something that has a very small amount, even this small amount is a mountain of oxygen 18. So in some way you have to try to reproduce this effect. But it is just a guess. I'm guessing that these grains are coated. So I have some extra shell of solar system materials. Nothing is sure.
Sarah, just I resist to any comment about aluminum 26, but there is a question. I would like to know how much the initial abundances you start from affect the final ratios. I mean, if in the envelope, if the stars is born with 10 times lower aluminum 27, the grains still remember which was the initial composition or not? At which level?
In principle, they do not. Because what's the problem? The problem is that grains are produced more or less at the very end of the stellar life, not at the, or at least the amount of dust produced during the first part of the red giant phase is very small. So at this point, you start to be very far from the initial composition. Because as you can see, in the inner region of the star, of the shell, we have an aluminum 26 on 27 abundance that is close to 0.7, okay, 0.8, then it's dependent a bit on the stellar mass. Outside, you have almost nothing. So even if you have 1 in 10 to the minus 3, that is still a huge amount of aluminum 26, maybe due to a campaign. When you start to mix a material that is the 3 order of magnitude richer in aluminum 26, you start to.
So if you would make the experiment that after the secondary jump, you put to 0 the amount of aluminum 27, the results will be more or less the same.
Yes, I just need 1 thermal interpulse more, so 10 to the 5 years more to reach that final value, but
okay.
nothing.
Okay, thank you.
And that's because you're doing ratio.
Sarah, coming back to these contamination effects that we just discussed, I know it is difficult to do that, but we are discussing also grain formation for massive stars and grain destruction, which is a big problem for massive stars. Is it? Do you have some measurements that show us that AGB stars form grains in the same way, independent of their mass? Because that underlies your interpretation, right?
Okay, I'm not an expert in that. When I discuss about that with Nan Liu or other colleagues in my department, that they say, okay, the difference in the temperature you have between very low mass stars and intermediate mass stars in their envelope essentially are too small to say we will have grains of different dimension. So for sure, we can differentiate for grains that come from massive stars and low mass stars. But says that a grain form in the envelope of 1.5 solar massive stars and 3 solar massive stars or 4 are different, this is very difficult to be said.
Okay, but we
should
don't have
much more
measurements.
effect in silicate, but not in oxide.
Okay.
Maybe measurements are important, but I think that is something that also you have to very well know the crystallography of these kinds of crystals.
But this is why I thought measurements would tell you, because the theory arguments are always somewhat circumstantial.
Yes, we know that are different, but we have not able to disentangle when you are above a determined temperature stress, is difficult to say. At least for now. I hope that we will have a better answer.
ALMA doesn't help. ALMA observations.
We will see. Not for now. Maybe in the future.
Okay, thank you.
Other questions? For context, a pre-solar grain is about the size of a human blood cell. So thinking of that inside of a meteorite and pulling it out is an extraordinary thing, right? So other questions?